Chapter 3 Z-Transform. The Z-Transform is a very useful tool for presenting, analyzing, and designing discrete LTI systems. We will use it especially to find the frequency response and evaluate the stability of the mentioned systems. At first, we will start by defining a class of systems for which we can apply the Z-Transform. Then we will define it and examine some of its properties. Then we will calculate the Z-transform of an important group of discrete LTI systems, and finally we will consider its inverse. After this chapter, you will be able to determine whether the system is linear, time invariant, and causal by describing the time domain behavior of a system, find the Z-transform of a sequence of finite length, write the transfer function in terms of Z for FIR or IIR systems from the difference equation, also find the corresponding signal in the time domain from the existing Z-transform. Right. LTI systems, in brief, they have two properties of linearity and time invariance or shift invariance. Linearity. A linear system obeys the law of superposition. If y1 of n is the response of the system to the input of x1 of n and y2 to the input x2, then the output of the system to the input of the form a1 times x1 plus a2 times x2 of n will be equal to a times y1 of n plus a2 times y2. Note: all real systems are nonlinear for some input. For example, when the input exceeds the linear operating range of a circuit. However, we are particularly interested in investigating the behavior of a system in a known range of input where the system is linear. Time invariance, the second property. A system is time invariant if a certain delay in the input results in the same amount of delay in the output. If y of n is the output of the system for the input x, then the output corresponding to the input x of n minus 1 will be equal to y of n minus 1. The same shift both in input and output will happen. Real systems are likely to change, so no system is absolutely time invariant. However, we are interested in examining the behavior of the system during a predetermined time range. For example, when the input is present. Causality. A system is causal if the output is 0 before the input is applied. Practical systems are causal. Impulse response. The impulse response of a system h of n is the output of the system for an input in the form of delta of n. Using the properties of linearity and time invariance, we can show that the output of an LTI system is equal to the convolution of the input and the impulse response of the system. Stability. A system is stable if its impulse response is such that ab sub h of n is absolutely summable. If the length of h of n is limited or h of n tends to 0 as n increases, this condition is established. Later we will see that the first term is related to FIR filters and the second one stable IIR filters. Anyhow, Z-transform. It's defined as h of z is equal to sigma n from minus infinity up to plus infinity h of n times z to the power of minus n. Very important equation, where z is a complex number. For a causal system, h of n is 0 for negative n. Since the z transform is a power series with an unlimited number of sentences, so it has a region of convergence denoted as ROC, region of convergence. In this area, the value of h of z is limited and cannot be infinity. This area is determined by the properties of h of n, or equivalently the properties of h of z. Computing the frequency response from z transform. Considering that z is equal to r times e to the power of j omega, we will define r being equal to 1, and it will suffice the condition. So r here should be equal to 1, then everything will be converted from z domain into frequency response of the system. Okay. Find the z transforms of the causal systems, also right-handed sided systems, h1 of n being equal to inside curly bracket 0.9 to the power of n u of n, and the second one h2 of n being equal to minus 0.9 everything to the power of n times u of n. Okay. Right-handed signal being plus 0.9, and the second one minus 0.1, again right-handed side or causal. Okay. h1 of z will be equal to 1 over 1 minus 0.9 times 0 z to the power of minus 1, or will be equal to z over z minus 0.9. OC apps of z greater than 0.9. For the second one, h2 of z will be the same numerator, 1 over 1 plus 0.9 z to the power of minus 1, or 0 over 0 z over z plus 0.9. The same ROC. Okay. It's said that the first system has a 0 at z equals to 0, and a pole at location 0.9. The second system's 0 is again at 0, but its pole resides at minus 0.9. Okay? Just put the denominator being equal to 0, then you will find the roots. Now, here you see ROC of the first system. This is 0 of the system, and this is the pole at 0.9. Green area shows ROC. Of course, it's beyond the figures from here up to, say it, infinity. Okay? What about the red one? The red circle shows unit circle, where r is equal to 1. We said it earlier. Okay? So you see here, again, repeating 0 and poles of the system. What about the second one? Okay, again, the same ROC, 0 similar, but this time pole has happened at minus 0.9. Okay? As ROC of both transfer functions include the unit circle, they will have frequency response and also stable. They will be stable. Now, putting R equals to 1, we will have frequency response of both systems, H1 of omega being equal to 1 over 1 minus 0.9 times e to the power of minus j omega, and H2 just plus here. The rest is similar to the first one. Okay. Now we have plotted the frequency response. For the first system, we notice that it's a low pass filter. You see here, the high frequency is pi. Here the plot is, of course, omega over pi. 1 means here is pi, and here 2 pi being equal to fs. Here is fs over 2. Anyhow, you see here, lower frequencies can pass, but there is considerable attenuation for higher frequency. When a signal is passed through this system, okay, because their spectra will be multiplied in frequency domain, and something near zero, if it's multiplied by the spectra of the input signal, it will truncate the higher frequencies. So it's acting as a low pass filter. Anyhow, later we will be more familiar. What about the second system? We notice that it's a high pass filter. You see here, higher frequencies can pass, but lower frequencies are not permitted to pass. So it acts as a high pass filter. What was the difference between these two systems? The first one's pole was in right-hand part of the circle. You see here, in here, the pole is here, so it's low pass filter. But for the second one, the pole resides in the left-hand side of the circle. Is it by chance or it's a rule? Later we will be more familiar. Okay. Now, another two important systems. This time, find the Z transforms of H1 of n being equal to 1.1. Okay, just have a pause here. The earlier one was 0.9 inside the unit circle, but this one is 1.1 to the power of n, u of n. The second system minus 1.1 to the power of n, u of n. Okay, using the equation for Z transform, we will find that H1 of Z is equal to Z over Z minus 1.1. This time ROC will be abs of Z greater than 1.1. Okay? What about the second one? H2 of Z will have a 0 at the origin and a pole located at minus 1.1. Again, ROC is similar. It's said that the first system has a 0 at 0, Z equals to 0, origin of the figure, and a pole at Z being equal to 1.1, figure 3.4. Okay? So, this is the pole of the system, and ROC will be greater than it, extended up to big area. Just we have concentrated in very small portion of ROC to fit inside the figure. You see here, this time ROC doesn't contain unit circle, red one. So you cannot define frequency response where R can be equal to 1. Can it be? No. For this system, there is no frequency response, so even it's not stable. Now going back here, if n approaches to infinity, you see here it's not stable. It's not converging. Anyhow, the same idea for the next one. Here the pole is here and ROC doesn't contain unit circle. Now, the second system's zero is located at the origin and pole at minus 1.5. ROC for both is abs of z greater than 1.1. Since the pole is outside the unit circle, the convergence zone doesn't include the circle with radius 1, so the system will not have a frequency response. Also unstable. It's unstable. It's understood that for a causal and stable, both causal and stable system, all poles should reside inside the unit circle. Okay. Now take home 3.1. Find the z transforms of h1 of n being equal to 0.1 to the power of n u of n, and the second one minus inside the bracket minus 0.1 to the power of n u n, and provide similar plots for poles, zeros, ROC, etc. we just mentioned for the earlier examples. Okay? The next part. What about their frequency response? If they exist, determine their types. Which one is low-pass filter? Which one is high-pass filter? And another important part, compare them with the frequency response in figure 3.3. Which one acts as a better low-pass or high-pass filter? Criticize the discussion. Now, proposition 3.3. Find the z transforms of the non-causal, also left-hand-sided systems. The first one, h1 of n, is equal to minus 0.9 to the power of n, u of minus n minus 1, and the second one, minus 0.9 to the power of n times u minus n minus 1, left-hand-sided or non-causal. Now, solving the z transform will lead to h1 of z being equal to, you see here, similar transfer function, z over z minus 0.9, but this time ROC is abs of z less than nothing, not greater, less than 0.9. And for the second one, similarly, the same and similar transfer function, z over z plus 0.9, and again, abs of z less than 0.9. It's said that the first system has a zero at z equals to 0, or the origin, and a pole at z being equal to 0.9, figure 3.6. The second system 0 is at origin and the pole is at minus 0.9. ROC for both systems is abs of z less than 0.9. Here you see ROC not including the pole but less than it up to small parts. Okay? So the first deduction, ROC can contain zeros but cannot contain poles because poles reside in denominator, and if they are going to be zero, so the whole fraction will be infinity. So you can never find ROC including poles. Okay. For the second system, illustration, zeros and poles of H2 of n being equal to minus 0.9 to the power of n u minus n minus 1. As ROC of both transfer functions do not include the unit circle, okay, they will not have frequency response, also not stable. Okay, so there is no frequency response for these two systems because ROC doesn't include unit circle, doesn't contain it. Okay, what about the next example? Find the Z transforms of H1 of n being equal to minus 1.1 to the power of n times u minus n minus 1, and the second one minus 1.1 to the power of n u of minus n minus 1. Okay, similarly, the transfer functions will be z over z minus 1.1 and z over z plus 1.1. For both, ROC will be abs of z less than 1.1. So you see, ROC contains unit circle. This time we will have frequency response and it will be stable, but the system is non-causal. Okay? Since the pole is outside the unit circle, the convergence zone includes the circle with radius 1, so the system will have a frequency response. It's understood that for a non-causal and stable system, all poles this time should reside. Of course, here there is a typing mistake. Oh, no. All poles should reside outside the unit circle. That's correct. Okay. Now, find the Z transform. The next example, find the Z transforms of H1 of n, H2 of n, and H3 of n. Okay. H1 of n is equal to 0.1 to the power of n, u of n, plus 0.9 to the power of n, u of n. A second order system. So H1 of z will be similarly, we mentioned it earlier, 1 over 1 minus 0.1 z to the power of minus 1 plus 1 over 1 minus 0.9 times z to the power of minus 1. Or similarly, 2 times z multiplied by z minus 0.5 over z minus 0.1 times z minus 0.9. The greater radius for pole is related to 0.9, so abs of z greater than 0.9 and abs of z greater than 0.1 will result in abs of z being greater than 0.9. Okay? Now, for the next system, H2 of n, this time, please be careful. The first part is similar, right-hand sided, but the second part is left-hand sided. Okay? So, what will be transfer function? The same transfer function, but ROC should be less than 0.9 because for 0.9 it's left-hand sided, but for pole 0.1 it's right-hand sided. So abs of z will be greater than 0.1 and less than 0.9. What about the third case? For both, we will have left-hand sided situation. You see here minus and left-hand sided, u and left-hand sided. Okay? Again, transfer function will be the same, but this time abs of z will be less than 0.1. Here we have considered the plot for poles, 2 poles and 2 zeros. Okay? If we had 2 poles at the origin, it was enough to write just 2 here, indicating that we have 2 zeros here. Or if we have we write 2 over pole situation, it means that we have 2 poles at the same point. Okay. Here, ROC greater than 0.9 for the first system. For the second one, you see here, ROC is greater than 0.1 and less than 0.9. And you see here, the unit circle is not inside ROC and we don't have any frequency response here and the system is not stable. But for the first case, ROC contains unit circle, so we have frequency response and the system is absolutely stable. What about the third case? Okay, ROC less than 0.1. It doesn't contain unit circle, so it's not stable and there is no frequency response. The deduction for a causal stable system, going back to the first one, for a causal stable system, all poles should reside inside unit circle. Okay? Now, properties of the Z transform. Delay. The delay in the time domain is equivalent to the following relation in the Z transform domain. x2 being xn minus 1, we will have z to the power of minus m times x of z. So that's the effect. A shift, a delay, will lead to z to the power of minus m times x of z. It means the absolute value of x of z will not change, but the phase will change for frequency response or for Z transform. Anyhow, convolution. For an LTI system, the response to an input x of n is equal to the convolution of the input and the impulse response in the time domain. Y of n is equal to x of n ast or convol with h of n. Meanwhile, Y of z is also obtained by multiplying x of z by h of z. So convolution in time domain will lead to the multiplication of their z transform. Okay? H of z is called the transfer function of the system. Right. Multiplication of two sequences in the time domain. Okay? If we have multiplication, this time in time domain, it will lead to x of z being 1 over j times 2 times pi, a closed contour integration over it, x1 of v times x2 of z over v times v to the power of minus 1 dv, where c is a closed contour containing the origin and located between the common convergence region between x1 of v and x2 of 1 over v. Contour or contour, you are familiar with it. The derivative in the z domain. Okay. We have x of n and x of z. If we multiply x of n by n, then it will lead to a derivative in z transform domain. Will be minus z, okay, times dx of z over dz. Now, relation between dft and z transform. Z is a complex number that can be written as z being equal to r times e to the power of j omega, meaning that dtft is considered. If we take r being equal to 1, we have dtft, and we know the relation between dtft and dft. So we will find the relation between z transform and dft. As a result, the dft values correspond to the values of z transform, which are located on the unit circle and at the angles equally distance, omega being equal to 2 pi k over n. That's it. Very simple.